Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. In the previous lecture, I was talking about A Student's Guide Through the Great Physics Texts, Volume 3, Chapter 8, in which we discussed Ampere's work on, well, we've been talking about Ampere's work on electricity, the flow of electricity, electrical currents, and the magnetic effects that it produces. In this lecture, I want to draw out, I guess, in the fullness, the magnetic effects that these electrical currents can manifest. So you might remember in the previous lecture I focused on an experiment that Ampere carried out in which he allowed an electrical current to flow through two wires that were parallel to one another, and he noticed that these wires attracted or repelled one another. They attracted one another if the currents were parallel to each other, and they repelled one another if the currents were anti-parallel or flowing in opposite directions to one another. That brought us up to about page 89 or 90. And so let's talk about some of the last few comments that Ampere makes at the end of this article. One of them is an interesting remark he makes about the invention of the telegraph. That's right. So if you look on the top paragraph on page 90, he mentions that following up the success of the experiment which was suggested to me by the Marquis de Laplace, by employing as many conducting wires and magnetized needles as there are letters, by fixing each letter on a different magnet, and by using a pile at a distance from these needles, which can be joined alternately by its own ends to the ends of each conductor, we may form a sort of telegraph by which we can write all the matters which we wish to transmit across whatever obstacles there may be to the person whose duty it is to observe the letters carried by the needles. So what is he talking about here? Let me make a sketch to help explain this. This is, remember, written in 1820. Here is a diagram. You might imagine one would have a battery set up like this. I'm going to draw our standard kind of 12-volt car battery like this with a positive and negative terminal. And you might imagine that the positive terminal is hooked up to a wire, and this wire has a break in it at some point. And that break, there's another wire that can fit into that break, that opening, and to that wire there might be a button. And on this button, there might be a letter, like the letter A, for example. This isn't exactly how Ampere describes it, but this is how I'm imagining it. That wire can be transmitted then. That wire can go across some long distance. I'm going to draw some kind of a break here, saying this could be a long distance wire. And then it could come back to the negative terminal of the battery, like this. And then above the wire at this distant location, one could have a compass needle, like this. And then you would have the letter A typed on a sheet of paper over here. So what's the point of this? You could have one person in, let's say, Paris, and another person in Lyon, let's suppose. Remember, this is in France. And this is hooked up to the positive terminal of a battery, the negative terminal. The person in Paris could press the button A, completing this circuit. Electrical current would go through this, and then the moment the electrical current passes through this wire, which is almost instantaneously, there will be a deflection of this magnetic compass needle due to the current flowing through it. That's something that both Ørsted and Ampere had mentioned, and that would lead to a deflection of this compass needle pointing to the letter A. So someone standing in Lyon would recognize instantly that the letter A has been transmitted from Paris. You can probably see where I'm going with this. If you have another wire with another break here with the letter B on a key up here, here's the letter B. I know it doesn't look so much like the letter B, but I'm trying to fit it in there. And then this wire continuing like this, going to that back like this, and then there's a compass needle above this wire, and a letter B perhaps typed on a sheet of paper next to that. And likewise with all the other letters of the alphabet and perhaps spaces and so on. So by pressing various letters, one could transmit a message from one place to another. So this is a practical application of the kind of experimental observations that Ampere and Ørsted, for that matter, were carrying out. So I thought that was an interesting point that Ampere makes. Okay. Now, there's one final point that I think is very interesting at the end of this article. And this is at the bottom of page 90, where Ampere says, we now turn to the examination of this last action and of the action of two magnets on each other. And we shall see, and this is the important point, we shall see that they both come under the law of mutual action of two electric currents if we conceive one of these currents as set up at every point of a line drawn on the surface of a magnet from one pole to the other in planes perpendicular to the axis of the magnet. Okay, so what is he talking about here? Remember, he had just gotten done explaining how his experiments demonstrated the fact that if you have two parallel current carrying wires, so a current in wire 1 and another current in wire 2, that there is a force acting on these, and that force will attempt to attract these wires. Oops, let me draw it in a different color, maybe make it a little bit easier to see what I'm doing here. So if there are parallel currents, there is a force of attraction between these two wires. And on the other hand, if there are anti-parallel currents, and this is what I mentioned a moment ago, if they're anti-parallel currents, then there's a force of repulsion between these two wires. Now, what does this have to do with magnetism? Well, Ampere has a theory, and the theory is this. We know that a bar magnet has two poles. So let me draw a bar magnet right here. And let's suppose the top face is a north pole, and the bottom face is a south pole. And let's suppose we put another bar magnet just beneath this one. And likewise, let's put a north pole on the top and a south pole on the bottom. Now we know since the time of Gilbert, and in fact many years before Gilbert, that these two magnets will feel a force of attraction to one another. Why? Well, north poles and south poles attract one another. So the top one would feel a downward force, and the bottom one would feel an upward force. So they attract one another. Now the question is, why? Why do these two magnets attract one another? It's simply an empirical observation that they do, but what is it that causes this? Well, this is Ampere's theory. He says, suppose we consider that a magnet, a permanent magnet like this, is actually a stack of electrical currents flowing around the periphery of the magnet. So I'm going to draw once again this magnet. But let's imagine that this magnet has on the periphery of it, flowing around the outside, an electrical current that goes around in this direction. And then just below that you have another electrical current flowing around in this direction, and another one flowing around in this direction. So the magnet consists essentially of a stack of these electrical currents flowing around it. Okay, and now we'll draw another magnet down here. I mean, we can leave aside the point for the moment of how do these currents arise inside of the magnet or around the edges of it, but let's suppose that just for the sake of argument, we concede with Ampere that there really are these electrical currents flowing around on the exterior surfaces of these magnets. Why would he think that this is the case? Well, think for a moment about what this implies. Well, each of these is a current loop, a loop of current. So if we think about any loop of current, I'm going to draw a square loop of current like this, and another one like one in this magnet. The experiments that Ampere just carried out imply that these two loops of current would attract one another. Why would they attract one another? Well, think about segment 1 over here and segment 1 over here. They are both parallel currents, and parallel currents, as he mentioned, attract one another. So this is attracted to this. And likewise, if we consider segment 2 and segment 2, well, those once again are parallel currents, so they attract one another. Likewise, segment 3, oops, I drew that arrow in the wrong direction. Segment 3 and segment 3, they are parallel currents and they attract one another. And likewise with segment 4, which are parallel currents, and they attract one another. Now we've just been considering a single loop from the top magnet and a single loop from the bottom magnet, but if there are a bunch of loops, it will really just amplify this effect. And so the result, he says, is that these two stacks of current loops attract one another in exactly the same way that these two magnets attract one another when they're oriented in this way. So maybe these two magnets really are just stacks of electrical currents. Well, what about repulsion? I'm not going to go through this in detail, but I want you to think about how this might work out. If you have a magnet right here with a north pole on the top and a south pole on the bottom, and you put beneath it another magnet, but this one has a south pole on the top and a north pole on the bottom, well, what might that consist of? This magnet here is just like the top magnet in the previous example. So you have these currents flowing around in this direction. But what about this one? It's turned upside down. That means the current is flowing around in the opposite direction in this one. You can just kind of imagine taking the bottom one and flipping it over and saying which way do the currents flow. Well, notice now that in this one, you've got this current number 1 over here and current 1 over here. They're in opposite directions, which means that they would repel one another. So I know I told you I'd let you work through this on your own, but I'm giving you kind of suggestions for how to think about this. And likewise with the other segments of wire, so they repel each other. So this is the image that Ampere is presenting us with to explain the effect of magnets on one another in terms of this repulsion or attraction between electrical currents. It's an ingenious idea, but there are some problems with this idea. And let me just bring up a couple of the problems that I'm not sure if I don't think he brings up, but might come to mind as you're thinking about this. First of all, you might ask, where do these electrical currents come from? After all, the implication is that you've got an electrical current in this magnet. Well, normally it takes a battery, some kind of chemical reaction, to produce an electrical current. What is it that generates these currents, if indeed they do exist in these magnets? Secondly, we also know that when an electrical current is generated, eventually it dies away due to the resistance unless energy is continued to put into it. Unless there's a continuing electromotive force that's trying to keep it going, that electrical current will eventually die out. Well, it seems that iron, many magnets are made of iron, they do have some resistance to electrical flow. So unless one were to continue to supply energy or electromotive force, it seems that the electrical currents would die out. And yet magnetism seems to last indefinitely. It's a very persistent phenomenon. So it doesn't seem, one would need to have some kind of perpetual source of energy within the magnet in order to sustain these currents so as to maintain this attraction or repulsion between the magnets. So this is a further problem that arises in this. And really, to try to understand this, Ampere is onto something here, but to get a deeper understanding of magnetism in terms of the microscopic structure, that is what's going on inside of the magnet, that will have to wait until about the 1930s and the dawn of the quantum theory of matter. That's brought about with the work of Schrödinger and Heisenberg